I'd like to wrap up what we have learned so far. According to the previous slides, we have three types of states for state charts. In state charts, states are either basic states and superstates or superstates. Now, for any modeling technique, we do have the requirement to also model time, and this includes the need to model timers. Therefore, timers are available in state charts. In state charts, timers use a special graphical notation. It is this notation where we have this sawtooth-like thing at the top of this graphical symbol. In this state, we have a time which indicates the amount of time after which a timeout is taken. So if we do not observe an input of A for 20 milliseconds, we will be using this edge, which is labeled timeout, and we will have a timeout into this next state over here. We can use this mechanism in order to implement our answering machine, in order to implement this processing superstate in the answering machine. Let's suppose that there is an incoming call. As a result of this, we will be in the state where we are waiting for seconds for the owner to pick up the handset. If the owner doesn't pick up the handset, we will be going to the next state where we are playing some text.
Sorry, there's nobody at home. Please leave your name and a message.
And this will be followed by a beep. This will be followed by up to 4 seconds of recording. This recording will be finished either by a timeout or by the caller being silent. And this again will be followed by a beep. And after this beep, we will be going to this state which is labeled dead. We will be exiting this super state if the calling person returns the headset. So this is how we can use the timer. Now, so far we have used examples to demonstrate what we can annotate to these edges. Now it's the time to really look at the general form of what's available for the labels at such an edge. In general, we can have three different things there. We can have events. We can have names of events. Such events will exist only until the next round of evaluating this model. Any simulator will have to evaluate such a model, and such an event, after it's generated, it will exist only until this next evaluation. These events can be either internally or externally generated. That means they are either generated as a result of some transition in our model, or they can be generated in the, for example, physical environment. And then the second part that we can have here for the labels next to one edge is the set of conditions. Conditions refer to variables, to values of variables that need to be met if such a transition is to take place. Variables will keep their value until they are reassigned. So that means that in addition to these events, we also have variables at our disposal, and we can use them to keep track of certain values. And then the reaction part actually can be composed of two different things. We can either have assignments to variables, or we can create events. So as an example, we have this last line on the slide here. Service off would be an event. Not in, and now comes the name of a certain state, refers to a condition which we are testing, and then the reaction part in this case includes only the assignment to one particular variable. Now, this is the general form of the labels that we have next to the edges. Next, I have to describe the meaning of such state chart models. Now, for state chart models, one particular meaning was published. This particular meaning is called the state-mate semantics. State-mate refers to the name of one particular implementation of state charts. According to this state-mate semantics, edge labels have to be evaluated in 3 different phases. The first phase is a phase in which we evaluate the effect of external changes on events and conditions. We can have functions that have events and conditions as arguments, and these functions have to be evaluated so that the function results are available for the next phase. Then in the next phase, in the second phase, we compute the set of transitions that have to be made. In general, due to the hierarchical nature, several transitions can be made for each of the steps resulting from a certain input event. And also during this second phase, we are computing all the expressions on the right-hand sides of assignments so that we are well aware of the resulting value of all these values. The assignments are not immediately made. These assignments to the variables on the left-hand side of assignments are only made in the third phase. In the third phase, all these selected transitions become effective and the variables actually obtain their new values. Now this separation into these phases 2 and 3 is very important for the meaning that is normally associated with the state-mate semantics. It's important for generating a unique result, a result which does not depend on the evaluation order of, for example, the different substates of n superstates. Let me demonstrate what can happen if we are using these separate states, and I will compare that to the situation where we would be using only a single phase for this evaluation. As an example, let us consider a case where we have an n superstate, and when we branch into that n superstate, we will be assigning values of 1 and 0 to the 2 variables over there. And then in this n superstate, we are having transitions that take place for the same input, and then associated with these transitions we have assignments to these variables. Now I'd like to demonstrate what will happen if we have this two-phase evaluation of these assignments. First of all, we are assigning values to temporary variables that are associated with our variables that are visible to the user. And for example, let a prime be such a temporary variable associated with a. Now we have to evaluate the current value of b. The current value of b obviously is 0. Also, we do the same thing for b. So we have a temporary variable which is associated with variable b. Let's call this b prime. And we have a assignment to that temporary variable as well, and the old value of a is equal to 1, so we assign this 1 to that particular temporary variable. Now in phase 3 we have the final assignment to the variables that are visible to the user. So we have an assignment to this variable a, and variable a now is assigned to a prime, and variable b is assigned to b prime, which means that as a result the new value of a will be equal to what we saved there in the second phase will be equal to 0, and the new value for B will be equal to 1. Now let's look at what would happen if we would have a single phase assignment. If we would have a single phase assignment, then the following would happen. First of all, we would be having this assignment to A, which means we have an assignment to A, where we are using the current value of B, which is equal to 0. And in a single phase assignment, we would now have the assignment to B, which means we would look at the current value of A, and as a result B would be assigned a value of 0. So both variables would be assigned a value of 0 there. And now let's look at the other sequence of doing these assignments. Let's do the assignment to B first. So if we do the assignment to B first, then B would get a value of 1. And now we would be doing the assignment to A, and well, A would now also get a value of 1, so both variables would get a value of 1. This means that the result of these assignments would obviously depend on the execution order. So that is something which can be very boring in practice, because you could have two simulators, one doing the assignment in one sequence and the other simulator doing the assignment in the other sequence, and both would generate what is considered the correct result. Now this can lead to real headaches of designers. You are designing a system and you come to the conclusion that you have two simulation runs for the same input and you would get different results, and you would then really have to start thinking and have to figure out what's the reason behind it. Now therefore it's superior to have these two phases of the evaluation to have reproducible behavior for the simulators. Now this reproducible behavior, which in the particular case is resulting in the swapping of the values of A and B, actually reflects the model of clocked hardware. If in hardware you had two cross-connected D flip-flops and you had values in there, then with every clock tick you would be swapping the values there in these two registers. So that's what we would model in our StateCharts approach if we have these separated simulation phases 2 and 3. The same separation into two separate simulation phases is also found in other languages, especially in those that are intended to model hardware. Now, what I described so far just reflects the evaluation of one transition from one particular situation of our model to the next situation of our model. However, we can have several inputs, and therefore we can have a sequence of such transitions. Therefore, the overall evaluation of state chart models consists of a sequence of so-called steps. For each step, we are starting with what is called a status in this context. Normally this would be called a state, but the term state is already used with a different meaning here. So we are starting with a particular status there, and then starting from this status comprising values of all variables, comprising the set of active events, and comprising the current time, we will execute a step, and the step involves the execution of these three phases that I just mentioned on the previous slide, and as a result of that we would be reaching a new status. And this procedure would go on again and again until some stopping criterion is finally met. So we see that we are starting with a particular status, then we are executing these three phases, and we will then be reaching a new status. I have to mention that other implementations of state charts do not necessarily have these three phases, and therefore the result could actually depend on the execution order. So we see that in general other semantics of state chart like languages do exist. There are several proposals for describing hierarchical state machines. UML, for example, includes a proposal for hierarchical state machines. There is one tool available from our university, from our department. They all do not include the simulation in these three phases. This view on the semantics depends more corresponds more to a software point of view, because in software you're typically not using these synchronous clocks that you have in a hardware design. There are some simulators that allow you to turn on and off the multi-phase simulation. If it's on, then the simulation corresponds more to a hardware point of view. If the distinction in these different phases is off, then this corresponds more to a software point of view. Now in state charts, we have already seen the fact that we have variables there. Values of variables are visible to all parts of the state chart model, and we have just seen that the new values become effective in the phase 3 of the current step, and they will be obtained by all parts of the model in the following step. So that means for each step we are propagating these new values to all the instances where we are possibly referring to these new values. So that means that the state charts implicitly assumes a kind of broadcast mechanism for variables. No matter how large such a state chart model may be, new values are always propagated within one step. Now we could try to implement such a propagation even for a distributed system, but it would inherently be very slow. So therefore, implicitly, we are assuming a kind of shared memory-based communication. Even though it's never really explicit in the state chart description, implementing state charts for a distributed system would be very inefficient. So that means state charts is appropriate for local control systems, but not for distributed applications, for which updating of variables would take quite some time. Just as a reminder, I would like to highlight the fact that the events that we have just seen in the explanation of the semantics of state charts, they live until the step following the one in which they are generated. So they are what we would call one-shot events. We could also think of having a single flip-flop, and we generate these events. They are stored in the flip-flop, and with the next clock phase they are gone. Now, state charts are nice, but they also have a certain problem. A problem that is inherent in the definition of state charts is the existence of conflicts. The left part of the slide shows a conflict that is possible with most versions of and implementations of state charts. So in this case, if we would have an input of A, there is a question, would we take this transition or would we actually leave the superstate and take the other transition? That may rarely be dependent on the particular implementation, on the particular definition of the semantics of state charts. From my point of view, one should give preference to the exit from the superstates, because this would really allow us to simplify the description of exceptions. But there are other conflicts that are a little more difficult to detect. The conflict on the left-hand side would be relatively easy to detect. Conflicts like the one shown on the right-hand side are a little more difficult to detect, because if we had a value of x between 11 and 19, then there would be a conflict, and otherwise there would be no conflict. So that means the conflict really depends on the particular value of these variables, and such conflicts are a little more difficult to detect. Now, in this context, I'd like to explain a very important property of state charts. State charts, if they are free of the conflicts that I just described on the previous slide, are determinate. That means all simulators should generate the same result for a given fixed set of inputs, and also if we assume that that the timing of the inputs is fixed. Now this is what Kahn calls a system to be determinate. That means we are assuming, we can be sure that the semantics guarantees the generation of one particular result. There is no ambiguity there. Now others call this property deterministic. However, the term deterministic has quite a number of different meanings. Non-deterministic is used in the context of so-called non-deterministic finite state machines, where even flat finite state machines can be in several of their states at the same time. Then some people talk about so-called non-deterministic operators. Others call the same property probabilistic operators. This means that we have operators that will not always generate the same result. We could think, for example, of having an add operation that has some noise, where some of the digits can vary depending on the value of some random noise signal. Also, some people talk about non-deterministic systems if the behavior of systems is not known before runtime. So if just the precise timing behavior of a system depends on the time at which an input becomes available, these people would call such a system to be non-deterministic. And finally, there is the use of the term non-deterministic in the sense of non-determinate as used by Kahn. So in order to avoid confusion, we will call the property that I described up here, we call this property determinate. So we are saying that Kahn process networks under state charts under certain restrictions are determinate. So this is the question, this is leading to the question that I'm raising right now. Are state charts actually determinate or not? That means, are all simulators required to return the same result for a given input? We have seen that this separation into two phases is a required condition. If we would not have the separation into two phases, state charts could not be determinate. And we know that semantics other than the state-made semantics may be non-determinate. However, even if we have state-made semantics, there would be possible other choices of non-determinate behavior. There could be this choice between conflicting transitions. If it's resolved arbitrarily, then obviously the behavior of state charts would be non-determinate. And also, if we had conflicts such as the conflicts that you saw on the right side of that previous slide, then also we could have a non-determinate behavior of state charts. So we come to the current conclusion. For state-made, if we rely on this particular semantics, we would have a determinate behavior provided that there are no other sources of undefined behavior. That means if these conflicts are not a source of undefined behavior. So at this point in time, I'd like to evaluate state charts. There are some arguments in favor of state charts and some arguments against. A very nice feature of state charts is the fact that we have an arbitrary nesting of AND and OR superstates, so we can really describe systems in a very hierarchical manner. Also, there is a reasonably precise definition of the semantics in that paper describing the state-made semantics. And also there is a large number of commercial simulation tools available, state-made, state-flow, better state, and I think you will be able to find many more tools that in one way or the other implement hierarchical state machines. Also, for many of the tools, there are so-called backends, which translate this type of a description into software or hardware languages, and in this way we can start with a StateCharts model and generate hardware from such a model. There are also some deficiencies of StateCharts. The deficiencies include the ones that you see on this slide. It's obvious that StateCharts is not very useful for distributed applications. There are no program constructs, so if we would like to have very complex algorithms, they would be very difficult to describe in StateCharts. Also, like for most of the other languages, there is no way of describing non-functional behavior. We cannot formally describe the disposability of the system under design. There is no object orientation, so dealing with very large systems might be difficult. There is no description of structural hierarchy. And in many of the cases, the generated programs may be inefficient, especially in the early days. These different substates of and superstates were translated to independent threads at the operating system level, which of course was a very inefficient implementation. Now, in order to remove that problem, in order to remove the problem of not being able to describe a structural hierarchy, there are frequently extensions available. There are so-called module charts which are available to solve that particular problem there. So we see there are some nice features of StateCharts and also some limitations. Now, the limitations do, of course, include, we see this on the previous slide, do include the fact that we have no program constructs available. And this means it's very difficult if we would like to describe very complex algorithms. Now, suppose that we would like to describe rather complex algorithms where recursion would be nice to have, where for loops would be nice to have. What could we do? Well, one approach would be to try to use the standard languages that you are familiar with, C, C++, Java, etc. But we do know already that there are some problems with these languages. We might have deadlocks. Also, in this context, if we look at the way that we can refer to time, we have a problem there because it's very difficult to figure out at what point in time a certain evaluation in such a language would take place. If, let's say, for example, we had a wait statement there in any of these languages, then we would just know how long that particular thread would be waiting, but we would not be really sure after how much time that thread would actually resume. And therefore, we call such languages asynchronous languages. Now, in order to get around that limitation, in order to get around the limitation that for these asynchronous languages, we don't really know precisely at what point in time we are executing these operations, so-called synchronous languages have been proposed. Now, synchronous languages try to combine the best of two worlds. On one hand, they are based on programming languages, so therefore it should be possible to describe complex algorithms, and on the other hand, they are based on automata, so that we can precisely refer to time. And this is also visible from this description of synchronous languages as it has been phrased by Nicolas Halbwachs. According to Nicolas, synchronous languages are based on automata models. Synchronous languages aim at providing high-level modular constructs to make the design of such an automation easier. So you see very precisely the idea is to describe automata, but to do this with techniques based on what you have available in programming languages. Synchronous languages describe concurrently operating on automata. When automata are composed in parallel, a transition of the product is made of the simultaneous transitions of all of them. And I'd like to demonstrate this using this little animation. where we see these communicating finite state machines. Let's assume that initially they are in a particular state. Now they are all referring to the same clock. That means if there is a clock transition, we will have a particular if we have a certain clock transition there, all these automata will have the corresponding transition. And all these transitions will be referring to the clock that we are using there. So these synchronous languages implicitly assume the presence of a global clock, and at each clock tick all the inputs are considered new outputs and states are calculated, and then the corresponding transitions are made. Now with synchronous languages there is a special way in which we are dealing with time there. In general, our system has to compute some function of the input. Let's assume that we have some input, some sensor input, maybe x, and based on that input we are computing some function, say f. Now for computing this input we have a certain delay that's required. We don't have any devices that compute functions in zero time. So there is a certain delay involved with such a computation. We call it capital delta of this function. Now instead of dealing with the real delay, we are typically happy if we can deal with some extraction of the real delay, because the real delay may be very difficult to compute. So therefore, instead of working with capital delta, we work with lowercase delta. And then we are considering the composition of components of embedded systems. And if we are connecting to systems that are computing functions h and g and j, we would then be concerned with figuring out what the delay for such a computation might be. And we know that the sum of the delays of j and h would be a safe upper bound on the delay of f. Now, whenever during the design we argue about the delay for computing such functions, there are two possible solutions. One solution would be to always assume that delta is equal to 0, and if we make that assumption, we are calling that situation, that type of design, a design with a synchronous language. On the other hand, we might be assuming delta to have some value different from 0, hopefully a bounded value, and this would be calling a design using asynchronous languages. Now the design with asynchronous languages doesn't really work. At least that's the phrasing of those researchers that are promoting the use of synchronous languages. And in order to demonstrate that asynchronous languages don't really work, examples that are used are typically based on the missing link to real time. So for example, if we had such a call to a wait primitive, we wouldn't really know after how much time we would actually resume the execution of that thread. And that means it would be very difficult to really figure out when a particular computation would be performed. Now with this assumption that functions are computed in 0 time, we are coming to a very abstract synchronous behavior. So under that assumption, automata would be computing their output in 0 time. That means if we have an input to some automaton, that automaton would provide its output in 0 time. And whenever we have an input there, the result would be computed in 0 time. That means the output is available immediately. That's our abstraction. And we are using this in the composition of behaviors. So if we have two finite state machines, one connected to the other, then the first one is providing its result in 0 time, and the second one is also providing its result in 0 time. Now this of course is an abstraction. In practice there will be some delay, But I think one of the key ideas of using synchronous languages is to work with that abstraction, and then in the second step to verify that this abstraction is valid. In order for this abstraction to be valid, we have to prove that the real delays are always shorter than the clock period. So we are using this two-phase design in order to free ourselves from the consideration of actual times during the first step. Now these synchronous languages, they require a broadcast mechanism for all parts of the model. You have seen already that we require new outputs to be available immediately. So this means that there is a certain idealistic view of concurrency. We have to verify that this idealistic view is indeed justified. The approach that I presented for synchronous languages has the advantage that in this way we guarantee determinate behavior. We are not really concerned with the different delays that might be associated with threads that are available in asynchronous languages. In a way, synchronous languages are the next step after the introduction of state charts, because synchronous languages combine the power of state charts with programming languages. And according to Nicola Halbwachs, state charts is almost a synchronous language. According to one conversation that I had with him, he thinks that immediate communication is the only lacking feature which would make state charts a fully synchronous language. Now, with respect to synchronous languages, there is one explanation appropriate, and it's the fact that for these synchronous languages there are different flavors. For synchronous languages, the implementation model is that of a finite state machine. However, the specification may be using a different notational style. There is what people call an imperative style of synchronous languages, and as an example, we can refer to the language called Esterel. For Esterel, the instructions look very much like instructions in a standard procedure language. However, the underlying meaning can be explained more or less only if we refer to the underlying state machine. Then there is also a different syntactical form in which we can describe these automata. We can describe these automata also in a graphical notation. This would then be called StateCharts. And there is also a way of describing the underlying automata in a data flow manner, where we describe how data flows through a system. And as an example, we can use the language Lustre there. And then there is a commercial implementation. For this commercial implementation, the users wanted to have all the preferred features available in one language. So the SCADE system, as a result, is a mix containing all these elements that I mentioned for the first three items. Regardless of the notational style, the specification always maintains a very close link to the underlying finite state machine, and the fact that we are referring to an imperative notation over here doesn't mean that we are close to von Neumann languages. In order to demonstrate that this is really practical, I'd like to refer to the commercial SCADE product that's available from a company. The SCADE product has been used in practical design. So, for example, many of the more recent designs by Airbus are using the SCADE product in order to generate software for aircraft. This is an instance of model-based design, because we are starting with the specification of a system in the form of synchronous programs, and the actual executed code is then generated from that. In this context, I'd also like to mention that Edward Lee, in the talk that I did already mention, refers to synchronous languages as one of the other options that exist for the design of systems. With synchronous languages, we can avoid the problems that are inherent in thread-based specifications. And he stresses the fact that for synchronous languages, the different tasks, or we could also say threads, are aligned to a master clock and to the sub clocks, and that the clock calculus is then used to check for consistency and deadlock. So in this way, we can very precisely know at what time certain computations are being performed. So this leads to the summary for today's lecture. Today I talked about communicating finite state machines. I introduced you to StateCharts. We saw that for StateCharts we are using hierarchical states in order to take into account one of the key requirements for designing embedded and cyber-physical systems. We saw that we have two types of hierarchical states, OR states and AND states. Also, we see that timers are available. We have seen that the updating of variables implies that we are using a shared memory there. Also, the way in which we decide which transitions to take more or less implies that we have a local non-distributed system. And then I introduced the distinction between the terms determinate and deterministic. And I said that for the property that we find for StateCharts, we will be using the term determinate. And then, in order to cope with the problem of specifying complex computations, but still being able to precisely refer to time, I introduced synchronous languages, which are based on a clocked finite state machine point of view. And as an abstraction, these synchronous languages are based on the assumption of zero delay, and this assumption must later on then be verified. This concludes today's lecture. Thank you very much. Okay, so ein paar Kleinigkeiten waren da drin, aber ich glaube, due to the lack of time, wir lassen das einfach mal so.
Ja, ich hoffe, der Ton ist gut rübergekommen, weil da gab es